right. Good morning, everyone. Thanks, Jose, for the introduction. My name is Renato Mio. I'm from the Brain and Behavior Laboratory. We have notes at the Imperial College London and the University of Bayreuth in Germany. And today I want to talk about how we're using machine learning to predict force for motor neuron spike brains, spinal motor neurons. So I know a lot of people here are working on the invasive side. We work non-invasive, and this is already an exciting time to be working on non-invasive neuromotor interfacing. A lot of people might be already familiar with the work from Meta. They have their neural wristband that can already decode gestures out of the box without calibration. This is great to decode categorical actions. In our lab, we previously worked as well. Sorry, can I have some help with the video, please? Thanks, Danny. In our lab, we also worked with kinematic decoding from EMG signals in the past, right? This is very useful also for assistive or prosthetic applications. Here we're decoding proportional movement, but for many other very fine manipulation tasks and in-hand manipulation, we require stability in the force control. We also require, and the needs of force control also comes from the properties of the material, like stiffness, deformation, right? So the point I'm trying to make is that we also need to decode proportional force. And that's what my talk is about today. And the natural, the way that we can do this more naturally for us will be to try to tap into the sources of the EMG signal, which are the motor neurons, the spinal motor neurons, right? And we do this by means of high density EMG. So instead of just having a relatively low number of EMG channels, we have now dozens or even hundreds of EMG channels that we can record non-invasively with these electrode patches. And there is also the technique, the blind source separation technique that we apply to this multi-channel EMG data known as motor unit decomposition. Maybe some people are familiar with this. So we go from the multi-channel EMG back to the sources, back to the motor unit spike brains that originally generate EMG signal. So the message here is that now we can decode motor neuron spike brains non-invasively, and we can use this to train our models to decode force. So we're not the first ones working on this, and I think this was mentioned probably also yesterday in a talk. So the way this is working in the literature right now, we go from the multi-channel EMG data, we decompose into spike brains, and then there might be a transformation of these spike brains probably to discharge rates, which is also what we're doing, and this will be the input to our regression models to predict force. Although some people also uses this for classifiers, like classifying gestures, for example. What we noticed in previous literature is that mostly they train either subject-specific or even trial-specific machine learning or regression models. And this, I think, is related to a limitation of the motor unit decomposition algorithm, which is that it converges to different sets of motor neurons in different trials or across different runs. This is a big limitation because this means that we don't have a stable input for our machine learning models. So then we don't have enough data to scale them. And we wanted to tackle this issue. So there are two ways in which we worked on this. One was to try to track the same motor neurons across different trials. And there are techniques for motor neuron tracking. We could do template matching with the action potential waveforms. This is something that actually we showed in our poster back on Wednesday. But today I want to talk about a different approach, which is to try to harmonize the inputs to our machine learning models in a way that we can decode force independent of subjects, independent of even the task. And we do this with the motor neuron spike brains as the input. So to first, as in any machine learning paper, we started with a data collection, right? We had 25 adult subjects for a data set, and we collected their synchronous finger forces and high-density EMG from the anterior forearm while they were performing an isometric finger flexion task following a force twist with trapezium shape, as you see on the screen. And we did this for 6 different conditions. 3 digits, so thumb, index, and middle finger, and 2 different force levels at the top of the trapezium force part. They did this for 5 repetitions, and so in total, we collected 750 trials. And then comes the part where we try to standardize all of our data for machine learning models. It's a lot of work. And we tested this on different machine learning models as well. The whole pipeline looks like this. I will try to break it down, and I hope I'm clear enough. So the first part is just more on the signal processing side. We have our multi-channel EMG data. We do EMG pre-processing, right? Like bandpass, notes, filters. And then we decompose it into spike trains. Then we have a set of spike trains for each trial from which we will derive our input features to our machine learning models, which is the next part. And we want to only keep the spike trains that are most correlated with force. So a trial will look like this after we sort of clean it, and we keep only the spike trains that are sort of correlated with force. From this, it would look like this. We only keep trials with at least 10 motor units, 5 early recruited and 5 late recruited. And from this, we will derive the discharge rates, which is now a continuous signal, the input to our machine learning models. We also wanted to compare with previous literature, so we also compute the cumulative spike train from all the motor units. And we want to test also for the level of detail in the representation for our machine learning models. So we also have an intermediate input, which is the cumulative spike train derived from early recruited and the one derived from late recruited motor units. Like I said, we are testing the detail in the presentation here. And these are our inputs for our machine learning models. We tested a battery of regression models from very basic linear regression to some nonlinear models, MLPs, and recurrent neural networks, and boosted trees as well. So what we got from this analysis, first for the decomposition pipeline, we had 128 EMG channels, but we could only decode from that 7 ± 5 motor units per trial. That is normal for upper limb muscles, actually, when you work with non-invasive EMG. The problem is that we could only include 166 out of all our trials when we applied our inclusion criteria. And these were the results that we got after feeding all of this into our machine learning models. Bear in mind, this is across all subjects and all task conditions. So the first thing we can see here about the performance by the coefficient of the R-square value, the coefficient of determination across different model architectures and different inputs. We have that the model strains on individual motor neurons were the ones that had better performance, and this was more prominent for RNN architectures. Here you see a sample prediction of our best performing model, which was LSTM in your case. And we also wanted to see what would happen if we had less motor neurons active. So as a sort of ablation, we randomly removed motor units, and we see a quasi-linear decay on the performance of our machine learning models, the top 3 in this case, as we reduce the number of motor neurons that we use to predict force. So, So bottom line, what we've done is basically because we didn't have sort of a baseline to compare, we tested the representation detail of the neural drive that we need to train machine learning models to predict finger pose. And we tested it on different machine learning architectures. So the main takeaways, we can predict very accurately, in our case, finger pose for motor neuron spike trains when we have this detailed representation of at least 10 motor units. And with this, we were able to outperform all previous attempts on this regression forecast. The RNN architectures were the best performing, but XGBoost was also actually kind of good when we had the cumulative spike train as an input. Most importantly, we were able to pull data from different subjects and different task conditions. And also by working at the motor unit level, we believe that this is a way that we can integrate heterogeneous data sets, which is great. And I'm sure all the people working on EEG can also know about the pain that it is to try to integrate across different electrode setups. But working at the motor unit level then gives us these spike trains, which are only temporal data or event data, if you want to say it like that. So then we could be independent of electrode setup and also independent of the muscles. At the time we submitted this, we didn't actually have the quantitative data to back up this claim. As of now, I can tell you that the model pre-trained on the forearm muscles can also work out of the box on leg muscles, and with fine-tuning, it works pretty well as well. So that's everything for me. I would like to thank my co-authors and founders, and these are our emails and our websites in case anyone wants to get in touch. Thank you.
Questions? There is one question over here.
Very impressive work, thank you. So you mentioned that the motor units, the activity varies from one trial to another. And one issue that can affect it is the stiffness of the wrist or the fingers. So I wonder if you took it into account, how did you deal with it?
So yeah, this was still under very limited condition. They were isometric finger flexion, right? So the people were fixed on the in front of the on the screen, and they were fixed to the table, sort of. I know that we should account for wrist movements later when we move more on the translational side. This is something that we're actually not doing at the moment. I know we have some colleagues in a kind of neighbor university, and that are working on that, and I know that it is possible, but we will probably need to scale on the number of channels. So as of now, this was done. This data set was collected last year. This year we collected a new data set with 52 subjects and 64 more channels, so 192 in total. And we work in the computer science side, so we do believe that scaling on the amount of data can lead us to account for all of that.
Thank you for your talk. So you mentioned that the performance can be improved with the selection of the model units. I wonder, how to do that in the real time?
Yes. So, sorry, was the question about the regression or the decomposition?
The decomposition and the selection in the real time.
Okay. Yeah. So this work was all offline, but for this analysis, we want to move to real time later. Motor unit decomposition can also work in real time. You just need one calibration trial. So you do one trial of motor unit decomposition, and you get some matrix that then you multiply by the EMG, and then you get the spikes in real time. That's how it would work in real time.
We have still time for one more question over here. Let me.
Thanks. I have two curiosities. So
Yep.
First, you said that your algorithms outperform other mentioned. So I was wondering whether also these studies use a motor unit or like bipolar EMG. And
Yes.
then the other curiosity was about why such a high number of trials had to be discarded.
Yes, those are great questions. And maybe, oh yeah, I still have control of this. Let me go back. Yeah, that. So for the first question, I only compare myself to other people working on force regression from motor unit spike lengths. There's some work that came out this year, so that wasn't included here. I think we still have better metrics. So I couldn't compare this to other people working in surface EMG because we're working with different inputs. We're working with the spike length. And then, yes, that is true. The reviewers actually said the same. Why are you getting rid of so much of your data? If you see the amount of motor units that we got per trial, it's 7 + 5. And we said, okay, we only have to keep trials that have at least 10 motor units. And luckily, I have some backup slides for that to tell.
No, please.
Oh, no. Okay, sorry.
This is not fair game.
Yeah. Okay. But right now, we already work in a different model architecture that can take variable numbers of inputs based on what the reviewers told us as well. It is working well. We have the same performance, and now we can take 3 times as many trials as before.
Thank you.